Today we are going to review, so it's algorithms, all right? So we're still kind of separating Tuesdays and Thursdays with practicing object-oriented design on Tuesdays, and Thursdays we're kind of spending more time on algorithms. So if you remember last Thursday, we talked about the quick search or binary search algorithm, and we talked about kind of how the algorithm goes, right? Finding that pivot, and then finding all the kind of splitting array. So got some homework. We started doing some stuff in the class. I think some of you already kind of got to a good point. There were some issues. So any questions on that? Was anybody able to get it working, or anybody stuck? Anything we can look at?
Mine worked. Remember last time it was non-functioning?
Yeah.
Turns out I forgot to put return statement.
Okay.
Yeah, I forgot to put return
yeah.
on the conditions of, yeah.
Nice. Yeah, it looked right last time when you showed it. I mean, I thought it was something small because overall it looked right. Do you mind going over it real quick so that in case anybody else is having problems, they can look at it?
Oh, I wasn't showing last time. Last time was Katya. I think
Katya was showing. Okay.
Yeah.
I thought that was you. My bad. So anybody wants to, Gia or Katya, you want to show the code? Anybody that has working code?
Yes, I kind of finished it last time, so
Did you fix that?
Yeah, I fixed it. I misplaced array.length with the middle index. So
okay.
Yeah, it was a stupid mistake.
Okay.
I can show.
That would be great.
Really quick. Where is it? Sorry, my son is here. So.
That's okay. Mine is here too, somewhere. Okay.
Okay, so yes, I just can run it, I think. Okay, here is my array, and we're looking for number 7.
Yeah.
And let's run it. And here we found it 7.
Yeah,
the index of array is 6.
Nice.
Okay, so let's find number, I don't know, number 2. Let's run it. Yes, we found 2 and the index is 1.
Okay. Can you quickly walk us through the code? How are you doing that? That's kind of the main thing. So.
Okay, let's see. Where is it? Binary recursion. Yes, so we are splitting the length by 2 each time we iterate. And once our target number is in the middle index, right here, once it's in the middle, then we found it. Yes, so basically that's the goal. So we just split each iteration our array by half, and we check one side of the array, then we split that side again, and then once we found our number in the middle, then we found it.
Yep. So that's your exit condition. Yep.
Yes.
Okay. So then if not, then you go to the left and to the right. Cool. Okay. Well, where was that? Somebody is waiting in the waiting room. Where was that bug last time?
It was here.
Okay.
I put middle index here instead of array.length. Yeah, because we start from 0 and finish this.
Okay, so you were going, instead of going to the end, you were going to like middle to middle, something like that.
Yes, yes. So it wasn't correct at all.
Okay, gotcha. Yeah. It's really easy to make typo there. So yeah, but yeah, pretty cool, right? How the binary, makes the recursion makes it easy to understand, right? So you basically have, like 6 lines of code, and that's all. That's all that there is. So it's
Yeah.
pretty cool.
Are we going to cover different types of searches?
Yes, today.
Okay, good, because I know there are a lot of them. I don't know why it's at school they do not. Okay. I'm sorry.
The future programmer is talking. That's okay.
Yeah. Future engineer, I think.
Future engineer.
Likes to build
Okay.
stuff. Yeah.
Okay. Well, he can help.
Yeah, sure. Because at the university, they do not allow us to use binary search. They always want us to use something different. I don't know why. Maybe they think it's too easy, or do you know why?
Which university?
University of Illinois. They like say at the computer science department, we don't use binary search. Just guys use something different. And I just Googled something, found something on Stack Overflow. Like there are different types of
I
search.
never heard of that. Yeah, that's
I don't know why.
Yeah.
Like be, simple binary search, simple one, like without recursion, like this one.
Yeah.
They do not want us to use it. I don't know.
Maybe it's because because the I don't know. Actually, I really don't know.
Maybe they are tired that all the students use one type of search, and they like, let's find something else.
Okay. Well, today, we just to correct what I said a little earlier, you asked about searches. So we're going to swap sorting and searches. So today we're actually going to look at kind of a binary sort algorithm. So, and then next class we'll do more searches. So we're going to be covering both searches and sorts. So they're kind of go hand in hand. So
okay,
cool. Well, thank you. This is good. So hopefully this is helpful. If anybody else didn't get a chance to do this, at least you can see how the program works, and hopefully this is helpful. So
yeah, I can take it if anyone wants.
Yeah.
Okay.
Cool. Excellent. Well, thank you. All right. Any questions on this? Hopefully this makes sense to you folks, kind of how this works, the algorithm, right? That's the main thing you kind of need to understand the algorithm here. The whole finding the middle element, and kind of searching on the left, on the right. And the obviously the most important thing is the condition for this is a sorted array, right? So having a sorted array is one of the things that may be a negative here, right? Because you may not always have the array in the sorted order, so that's could be a problem. So today,
I'm sorry, Igor.
Yeah.
Just a quick question so that I understand this right. In a sorted array, binary search method takes logarithmic time complexity. I don't know if I'm pronouncing it right.
Well, yeah,
but
you
it's
got it.
logarithmic,
Logarithmic.
right? Yeah.
Yep.
Okay. Thank you.
Correct. Yeah. And again, logarithmic, as you know, means that the time they're going to spend searching for an element is not proportionate to the number of elements. So remember that graph kind of levels off, right? So we add more elements to the array, but the time is just going to increase little by little, not proportionally like in ON. And ON is the linear search. And as you may remember, linear search is the basic search, just going for each element and comparing. In the linear search, you don't have to have it sorted, obviously, right? So, and you got to always remember, when you want to implement something like this, if you have a huge, very powerful machine, not a lot of elements or anything like that, linear search always works the best. That should be your default, right? Linear search, just going through elements, searching, comparing to each one. That's still a default, because the last thing you want is to introduce complexity. So the binary search is obviously, there is a complexity. You have to sort the elements, and then you have to implement that code. So it's a little more complex, right? So you have to justify that complexity. And like I said, sometimes if it's 1,000 elements and you have your computer, your server pretty fast, who cares? You're gonna do this in milliseconds anyway. So sometimes the actual the binary search is going to be more expensive because you have to sort the elements, right? You have to go into the database and sort the elements. We're going to take a look at a sorting algorithm now today, and kind of review that. So you could potentially use that. That's another greedy algorithm, or divide and conquer, which still gives you that logarithmic time, because it's cheaper than other searches, or more faster basically. But still, you got to be mindful of, basically ask yourself, do we really need this, right? Do we need a binary search? Because a lot of times you're just going to be fine, but sometimes you're going to need it. So. All right. So let me just share my screen. I'm gonna talk about sorting. So say you need to sort an array. So also a very, very common thing to do. So sorting an array. So searching, sorting, kind of two main use cases for algorithm. So today we're going to cover the quicksort. So quicksort is a kind of a main sorting algorithm. It's also, like I said, divide and conquer. Divide and conquer is sometimes called like a greedy strategy, divide and conquer, something like that. So algorithmic complexity, again, very similar to search that we just went through. It's faster than linear, and actually used in array.sort in Java. So this is actually a strategy that's used in your array.sort. When you call array.sort in Java, that's what Java is doing on the back end. So it's actually doing the quicksort implementation. Why learn it, right? Because you already kind of have it. Well, you kind of understand that it's again, like we talked about, right? When you want to become a engineer, right, rather than just kind of a programmer, the true engineer understands what's under the hood of the car, right? Because that's how you become really knowledgeable of what's going on. So it makes you in the long term a better developer, and you can certainly progress your career much faster than somebody that just has no idea how these things work. So even though this is kind of already implemented for you, it's good to understand what's actually happening, how computers sort values, right? So you kind of know this stuff. Plus, they ask on the interviews a lot, and especially in in big companies deal with a lot of data. If you ever want to work at a company that deals with a lot of data, they cover that stuff, because again, they want to understand whether you're just kind of a shallow type of a computer programmer that just went, opened the development interface, kind of learn few things about coding, some loops, or you actually understand a little bit deeper. So, you know, especially for you guys, as since you don't have a lot of experience, you know, that the deep understanding is what's, you know, what's going to be important. So all good stuff. So quick sort steps here. So again, the algorithm, remember, has all steps. So for you guys, you need to remember the steps, right? We talked about you know, steps here in our searches, and we kind of, you know, trying to pivot, dividing the array by 2, and then left and right, right? So we talked about that, and you know, so here, same thing. We were doing steps. So steps start with the same pivot selection. Anywhere you have this, anything that divides, divide and conquer means you divide your array in partitions. So same thing you're doing in the search, in the binary search, you're doing quick sort. You find some kind of a pivot, or you divide your array. So pick an element, call it pivot from an array. Here, usually it doesn't really matter which element you pick. Now, unlike the search, where you kind of divide the array length by 2 and you kind of get the middle element and then go left and right, here, the usual approach is leftmost or rightmost, so first or last. And I'll show you why, because it's just, you know, a little bit simpler. But, you know, in theory, you can choose any element. You can do the middle, you can do third, you can do, you know, so doesn't matter. But for this example, we'll do, you know, probably we can choose either or. We'll choose rightmost probably. So basically, you pick an element. For this example, we'll take the last element of the array. So and then you do what's called a partitioning step. So in partitioning, we reorder all elements of the array so that elements that are less than the pivot, and the pivot again is our value we picked in the array. So let's say it's the last element. So then in partitioning, we reorder the array in place usually so that elements that are less than the pivot number are on the left, and the ones that are greater are on the right, right? So basically, we're not ordering anything. We're just taking kind of an element, and then we're, you know, leaving everything that's less than the element on the left side of it, and everything that the greater, we throw to the right of it. And we do it in place. So, you know, there's going to be a little bit of a confusion, you know, how we do it in place. So I'll show you how we would do it if we're just adding to new array, but then in place, when it comes to implementation, you're going to see it's a little tricky, but, you know, you'll get used to it. We'll give you time to kind of get familiar with that.
So we're basically working only with indexes?
Mm-hmm. Yep. So you're going to have 2 indexes, right, Timur? So, you know, remember when we talked about how you manipulate arrays in place, we talked about you're always going to have, you know, you have to swap something, right? So you're going to kind of have 2 indexes, and, you know, you're kind of going to be going, you know, from the left to the right and from right to the left, and you're going to be finding things to swap. And then once some condition is met, you're going to actually swap the, you know, the last element, which is pivot, kind of in the middle. So what you're going to see is basically you're going to have, you know, after each path, the pivot is going to stay in the right position. So the whole point is to kind of keep breaking this whole thing and always putting that pivot in the right position. The right position means all the elements that are smaller are on the left, all the elements that are greater are on the right, until, you know, we basically have arrays of 1 element. So so that's kind of the recursion here. You're going to apply the above step to subarrays until, you know, until there is no need to sort anymore. So until you basically have single elements. So until there is no need to swap. So all of that is going to be done in memory. So I'm sorry, in place. So that's kind of the thing. Again, find an element, last first doesn't matter. Go through array. Usually, like I said, it's done in place, and leave everything that's less of the element to the left, greater than element on the right. So you basically kind of doing some sorting, right? And then you apply the same steps to the left subarray and to the right subarray, very similar to what we did with our this thing. So here we took the middle element, here we're going to take the last, and we're basically going to go through all the elements here and say, if you're smaller than the pivot, you're going to stay to the left of the pivot. If you're larger than the pivot, we're going to try to get you to the right of the pivot somehow, and we'll see those steps. Like I said, it's a little tricky because we're doing this in place. So, and then the pivot is going to end up in a position where all the values on the left are going to be smaller, all the values on the right are going to be larger. But that's the most important thing. We know that the pivot, we don't care if the values on the left or on the right are sorted against each other. Doesn't matter. That's the recursion is going to take care of that magically. All we care is the pivot. We sorted this element. It's not going to move anymore. So basically, all we care about after each iteration of the recursion is that the element that we chose as pivot is going to be in the position that it's going to be in. Because everything to the left of it is smaller, everything to the right of it is larger. So we know that that the pivot has basically found its place, right? And then we're going to go to the left of it and to the right of it, and then sort those, and you'll see, eventually they're going to just sort each other out, and things going to work out. All right, so let's kind of take a look at one example without really doing much of a worrying about how we're actually going to swap things here. So let's say, we have this array, right? And then we have the pivot. So in this example, we choose the last element as a pivot. And now we need to say everything, we need to make this array. So everything that's, less than the pivot is going to stay to the left. And then everything that the greater than the pivot is going to stay to the right. How do we do this, right? So, okay, well, let's see, what's less than the pivot? 1. So let's say we go down this way, right? So 1 is less, okay, it stays. -6 is obviously less than 3. All right, it stays. 8, we gotta move. I don't care right now. Let's not worry about how we're gonna move. But let's say we move to the, to the right of the pivot. 6, we're also gonna move. Right, so don't worry about how they kind of end up here. That's going to be the trick here, because it's in place, right? We're not really moving 8 here, 6 there, because this is we're going to do this in place. So bear with me a little bit, right? We're not really appending to the right. We're gonna do a trick here when we kind of go, through things. But for this example, let's just assume that somehow we're doing it, and basically, as you can see, everything that in this array that was greater, we moved to the right of the pivot, and that was smaller stayed on the left. All right, boom. So now, as you can see, the 3 is in its final position. This guy is in the final position. So this is the first iteration, first recursion function. Now, we basically say, okay, now do the same thing, but on the left side and on the right side. So pivot index -1, pivot index +1. So the index of the pivot is always going to be important, like in binary search. So here we're doing this thing. We're taking this subarray and that subarray. Again, we're doing this in place. So, we're not really splitting anything. We're just playing with indexes, which we'll see a little soon. But here, again, we do the same thing. Pivot always, same logic for the pivot, right? You can't change it. So the last element, and then we say, okay, well, let's go through this, and then everything that's greater got to end up on the right. So 2 ends up on the right of 1, and a -3, -6 stays here. Boom. So now, again, in this iteration, we have placed 1 in its final position. And then, we're going to do some recursion on this subarray. On here, we're going to do recursion, but quickly figure out that there is nothing to sort because it's one element in this subarray. Same thing is happening on the right of that 3, right? So, we got 8, 5, 9, 6 here, 6 being the pivot, and then we kind of throw in 9 over there and throw in the 8 over there, and then we have the same kind of situation. 5, we're gonna go back into the recursion and figure out there isn't really anything to sort because it's just, we're gonna see that the indexes, we're gonna do 2 indexes, and they're basically the same. So we're gonna hit our remember we talked about that exit condition, right, where there is nothing to do, like in the binary search where your pivot was equal to the element you're looking for. Nothing to do, right? So here, this is going to be the exit condition. Here, there's more work to do. So we're going to do the same thing here. 8 is going to be our pivot. And we're going to say, okay, is 9 greater than 8? Yep, 9 goes here. So we swap. These guys, again, using fancy indexes, 2 indexes to go through. And then we're going to basically, since it's a recursion, remember, this is all happening inside of one array. We're not splitting the array. We're not creating 1, 2, 3, 4, 5, 6, 7, 8 arrays. There's nothing to put back together. All of that is happening in swaps. So when this all happens, after you do all the swaps, this is what you're going to have. -6, -3, 1, 2, 5, 6, 8, 9. Right? So basically, all of these are done, using the swaps in array. So this is not, all of these are not individual arrays that we just created. So nothing to put together. You don't have to glue it all together. It's already in place. So that's the beauty of it. You don't have to, you're not breaking it up. You're not slicing arrays. There is no function to slice array in Java. So it's not that easy. So you're basically gonna end up with this once your recursion ends. Does this make sense, kind of on the high level?
Yes.
It is kind of makes sense, but I have no
Only
idea.
only on the
implement.
high level.
Yeah, I know. It's this one is harder, and like I said, I'll give you guys more time to go through that. Actually, we'll probably end a little early today because I gotta a little prior arrangement, but I'll walk you through kind of example with using the the actual algorithm, and we'll probably spend more time on that next week to firm it up, because I assume it's going to take a little bit time. It's much more complex in terms of implementation than the binary search. So all right, but remember, for now you got a pivot. You're throwing everything less than the pivot to the left, and then graded to the right, and then you're kind of going to the left and doing the same, going to the right and doing the same. So with that, let's go with this array. All right, so I prepared this exercise, and we're gonna kind of see how we're gonna implement this, right? So it's easy to talk about it. The idea is there, like you would know how to do this using like brute force, right? So brute force, I think you got it, right? It's not hard. You kind of keep doing that. as you were without the computer. This is kind of brute force. But how would that work if you were actually to implement this? Because the trick really comes, like I said, in place stuff. So let's look at this. So we have an array, and we're basically saying we need to, we need to start sorting that. And here's the, I'm gonna write up the actual pseudocode or algorithm. And again, all of this is available online. So you guys kind of, as you are getting used to it, you can look at it. So first we, let's say here we choose highest index. Right, so last, right, last index in array as pivot. And step 2 we're doing, and we're going to be walking through that. So let's do. So we're going to need to take 2 variables. Again, we need to be swapping. We can't just take this and then take like this value, throw it over here, because that's not how array works, right? You can't really do that because you have to create a new array and all of that business. So we need to be swapping. So how do we swap? We have 2 things that we're going to be doing. We have this side, and then we're going to have this side. So we have 2 indexes, right? So we got to take 2 indexes. The first one is going to be on the left side of array, and one on left of pivot, or left side of array. It's going to be beginning, and one on left of pivot. So we're going to say, we don't have a lot of choices here, right? So basically you take this one, and then we take this one. So array 0, and then array pivot -1 or length -1. So we're gonna kind of have 2 indexes there. So then it's basically kind of saying left points to the low index, and then right points. So we have left and low and high. So that's kind of, so this is going to be the low one, this is going to be high one. Okay. So now this is where the fun part comes. So we're basically going to have, okay, so what do we need to do? We need to kind of figure out how to swap things, so that we're going to be swapping, and we want everything. We want to be comparing to this pivot. How do we do that? Not pivot. We can't throw stuff here. That's a challenge, right? So basically, we're gonna start here, and we're saying the left one, while value at the left is less than pivot. So if the value at the left is less than pivot, move right. So we're saying, if things are less than pivot here, move right, keep going. So if it's less than pivot, don't mess with it. That's what we're saying, right? It doesn't matter, what it is, but if value is less, then don't pivot. So while value at left is less than pivot, move right. So don't mess with it. All right, okay, so far so good. Now, same thing here. We gotta have some kind of condition for our right or high index. So basically saying y value at right is greater than pivot, move left. So anything that's greater than pivot, we basically going to ignore as well. So if the values are greater than pivot, then we're going to continue moving. So we basically, as you're going to see, we're going to try to, soon you're going to see, we're going to try to insert a pivot somewhere. If you're, didn't get it yet, we're going to kind of have low values here, some high values there, and we're gonna really, what we're gonna do, we're not gonna move things beyond the pivot. We're gonna actually swap things where we're comparing, we're trying to put something smaller than the pivot here, some things that are larger than the pivot on the right side. And what we're gonna do is we're gonna try to insert the pivot in the middle. So we're gonna swap the pivot with some value here. That's how we're actually going to do the in place swaps. I know a little, weird to get. So, but that's what we got to do when we're doing this in place. So, to basically, again, we're trying to have smaller values on the left, larger values on the right, and then pivot is going to end up in the middle, right? That's where we're going with this. We didn't get it yet. That's why it's a little funky. But so while value at right is greater than pivot, move left. Okay. So I guess we'll see how that goes, right? So we're kind of leaving things. Now, when do we swap? Well, we swapped if they don't match. So basically, if both steps 5 and 6 do not match, so they're false, right? That's where we swap left and right. Okay, so if this is false and this is false, we don't move. Both of them have to be false, not one. Sometimes we're gonna move left and we're gonna pause the right. We're gonna say, this is going to be, this is going to be true. We're gonna keep going, keep moving this pivot here. J is gonna be stuck. Like the value here may be actually, smaller than the pivot. We're gonna stuck and we're gonna look what to swap it with. We're gonna wait till the left is also false. And then we're gonna swap. So you're gonna see that, we're gonna probably swap this and that, something like that, right? So we are kind of patiently gonna wait at one of the sides to see what we can swap. Now, I know, it's okay if you're confused. Hopefully we'll see how this works. If I don't mess up, it's not easy even for me kind of to do this on the example with spreadsheets. So I'll try. But again, if both of these don't match, false, then we swap left and right. All right, well, at some point we're gonna be swapping. We're gonna have elements on the left generally smaller, elements on the right generally bigger, and at some point we're gonna have to move this pivot in the middle. Okay, well, how do we do that? We're gonna do that. So if left is greater than equals to right? So if we kind of left jumped over the right. So where the point where they met is new pivot. So we're gonna move the pivot where they met. So left is going to jump over the right or vice versa. Now the where they met is gonna be the place where we're gonna bring the pivot. So at some point, we're gonna keep going. We may be swapping, and at some point, One of them, the left is going to go over the right. So the index, the left index is going to be greater than the right index, right? That's where, where they kind of met before, they jumped, is where we're going to bring this last, the pivot. So we're going to insert it somewhere. Here, it doesn't matter. So, hopefully you see the concept, right? We're kind of leaving smaller values here. We're leaving smaller, larger values here. We're swapping of here and here to make sure that roughly, they're kind of positioned, correct relative to this pivot. And at some point, we're going to try to insert the pivot in the middle. And then the pivot is going to be larger than everything to the left of it, smaller than everything to the right of it. And then we're going to do that same thing for everything prior and greater than the pivot. So far so good, kind of on the high level.
Yep.
Okay, all right, so let's see how this works. And again, if I mess up, then you guys can fire me, but it's not very easy to do on Excel. So I'd rather do this in the code. So so we have, let's say, I and j. So we're going to take two variables, I and j, and I is going to be 0. Let's say, and then the j is going to be the one before the pivot. So this is I 0, 1, 2, 3, 4, 5, 6, 7, 8. So j is going to be, let's say, 8. Right. So this is kind of, we're going to start. Well, so let's go through this, and then you guys can help me if I mess up. So beginning of array, I want to, so again, beginning 0 and 8. Now, if the I is going to be, so we're going to be incrementing them. Again, that's where, pay attention if I screw up, but let me know. I've tried to do this, several times with these classes, and you think I'll get it right, but I always mess up with some of the indexes because it takes like 5 or 6 iterations. So not very easy. So we're actually gonna look for the situation where the right, sorry, the left is equals to the right. So I needs to be equals or greater than j. So watch for this thing. So now we kind of did all this. So let's, while value at the left is less than pivot, move right. So is 35, I wish I could keep this here. And I wonder if I keep them side by side. You guys could see that.
You can copy the text inside.
Yeah, but this is Excel.
This actually works.
Yeah. Let's save this. Okay. All right. I think this is decent. Let's see if we can squash that a little bit. And move this. Move that. Oops, come on, little dude. Okay, perfect. So you guys can see this, hopefully, still, the steps. Yep, all right.
Yeah.
So the value at the left is less than pivot. So is this less than pivot?
I'm sorry, I missed what is our pivot from.
Okay, so pivot is 31.
Oh, 31, yeah, okay.
Wait.
No, it's more.
Okay, so then is this condition, do we move forward? We don't, right? We kind of stay here, right? So at the same time, we're doing, we're taking the j is 8, and we're saying, so this is kind of happening at the same time, right? So first we looked at the I and compared to the pivot, and we see, kind of from the brute force, we see that 35, comparing to the pivot, we want to move it to somewhere to the right. We don't know where, right? but we want to, it feels like it should be somewhere on the right side. If we were to sometimes, at some place insert the pivot in the middle, we want this thing to go somewhere to the right. We don't know where yet, but so it's a candidate to moving. That's basically what we just determined. It's a candidate, it's got to go. It's, it's got to go. So we don't want to ignore it. That's why we're saying we're not moving. Like, hold on, buddy. You're not in the right position. We got to move you. You're greater than the pivot. Now we look at here, 26, and we're saying, is the value at the right greater than the pivot? It's not, right? It's less than the pivot. So same thing here, right? We're basically saying this dude here, if the pivot was somewhere in the middle, this guy, it feels like it's got to go to the left somewhere. We don't know where the pivot is going to end up, but this got to be, it cannot be on the right. This is less. You see what I'm saying? That's kind of the logic here. So now we're saying if we actually hit a jackpot right away, if both step 5 and step 6 do not match, so they're both false, we got to swap them.
Mm-hmm.
Right? Hopefully it makes sense. So we're basically saying they don't belong. So we swap 26 in place. You guys know already how to do that. And then this guy gets 35, right? So we didn't do anything else. We just swapped those two. So 26 came here, 35 came over there. The rest is the same. So it feels a little bit better, right? Like, yeah, we don't know what 31 is going to end up, but we feel a little bit better about ourselves because we know this 35 came to the right, 26 came to the left. Things are looking up. All right, let's look at the next one. Okay, so we look at 33. Okay, so value at the left is less than the pivot. Is that less than the pivot?
Yes.
It's less than the pivot.
No.
33 less than the pivot.
No. Oh, yeah.
Okay. So so it's greater, right? So we're stopping here again, right? So we kind of move it. We say, nah, we don't like you. Now here we're at 44, right? We kind of moved down. So this one actually 1 and this one actually 7, right? 1 and 7. Sorry, I forgot to update this. And then we're at 44 and we're saying the same thing. Okay, is 44 greater than the pivot? Yep. So, remember, we're stuck. We're stuck on 1, right? 0, 1. This dude right here, it's greater. We don't want to move it. It feels okay. So this is the situation. We're stuck on the left. We're saying, this dude, we got to move. This dude, we don't need to move. We get to this dude here, 27. Do we want to move this 27?
Yeah, we want to swap them.
We want to swap this dude, right? So we want to swap. So we got, we moved to 6, right? 19 is obviously less than the pivot. And what do we swap this? This dude right here. So 19, 33.
Should be 27, right?
I'm sorry?
Shouldn't be 27.
Yeah, it should be 27.
We're swapping.
Yeah,
with
what happened with 27?
Oh, what did I do? See, thank you.
You fired.
I am fired already. See, I told you, every time I do this, I mess up something. Well, I'm glad you guys are, picking this up. That's the main, the most important thing. All right, so let's go to this again for my learning as a teacher. So we were here, we were trying to swap 33, right? We said 33's got to go. Because it's obviously greater than the pivot. And we were where? We were at 27, right? As you guys
Yeah.
pointed out, right? So, so what we need to be swapping is what?
33 and 27.
All right. So now it's 26, 42, and those haven't been touched, right? It's still there. All right. So cool. All right, well, things are looking up. So we got two things here. They're, smaller than the 31. We got three things here that are larger than 31. So, it seems like, we're making some progress. Some point we're going to be able to swap. So we are 1, 2, 3 on the, I haven't been updated that, but we are on 4, right? Oh, sorry, 0, 1, 2, 3. 3, I didn't update that correctly. And then here we are on
We're on 2, right?
So right now we will swipe 42 and 19, right?
Yeah, it should be 2.
Okay, so then we are 0, 1, 2. I'm sorry. So we are 0, 1, 2. So 42, as you already know, it's greater than the pivot. We got to swap it. And here we are at the 19 or 0, 1, 2, 3, 4, 5, right? The index 19. We are basically saying swap 42 and 19, same thing. Both steps are true. So 19 goes here. 42 goes here, 26, 27, 10 stays, 14 stays, 33, 44, 35. All right. All right, so so far so good. So
Yep.
all right, so 26, 27, 19, right? So we are at 3, right? So 0, 1, 2, 3, we're here. And then at the right, we are 0, 1, 2, 3, 4, right? So we kind of look at keep going on the left and keep going on the right. And here we encounter 10 as the next thing, and the 10 is obviously less. So we kind of say, okay, stay, right? We don't want to move 10. Okay. And then on the position 4, 0, 1, 2, 3, 4, are we here, right?
Yeah.
And we say, is 14 value at the right is greater than the pivot? Is it greater than the pivot?
Less.
Less. Okay. So do we move?
No.
We stay, right? So we kind of stuck at the 4. We're stuck here. The right index is stuck here. Our left index continues going. Nothing stops. So here's the trick, right? And you guys going to implement this in the code. I don't know how, but you will because you're all smart. So the trick here is, we stop the right one. The left one says, all right, well, I keep going, right? It goes to the 14. And then basically the left becomes 4. The right stays 4, right? So that's a very critical point here. So they met at 14, right? And it says, well, 14, it's now that's where they met. Remember, the right one is here because it's basically saying 14 is not greater than the pivot. I cannot move forward, or the loop is not letting us. The left one, it says, hell yeah, keep going. 14 is less than the pivot, keep going. But they met, right? They met at the element 0, 1, 2, 3, 4, right? Left and right are together. The left will still keep going, right? So they met here. So now this is the new pivot.
Do we need to split this array into
Nope.
like
All we need to do
imaginally?
Yeah, it's fun. Yeah. So basically, where they met is where the new pivot is. So we swap. So let me just double check. So this is where, let me just double check, make sure we're not. So here, so they met here. Let's see. So the 14. So the 34 gets swapped, right? So this one, they met here at the 4, and then the left keeps going, gets to the here. So the left greater than equals to the right, the point where they met is the new pivot. So basically, I believe it's actually here where the pivot goes, and then 42 comes here, and then the rest kind of stays like this.
But how it happened if they met at index 4? Why with index 5?
Yeah, so basically, you know, the right stays, but the left kept going. So it got to the next one. So basically, the next one is where you wanna kind of swap the you know, the pivot. So that's kind of, so we'll look at it in the code. We'll kind of look at the implementation. So I know it's a little confusing, and you know, the exact point is a little confusing. But what happens is you basically get, you know, the pivot, which is here. As you can see, we got to figure out, you know, what happens with the 4 here, 0, 1, 2, 3, 4. Now it goes to 5. So maybe it's what they met is the new point.
At this point, I'm sorry, Igor, we have 2 pivots at this point, right? 14 and 31.
Yeah, so this one becomes the new pivot. So this one, 0, 1, 2, 3, 4, 5, the position at 5 becomes the new pivot. So now basically what happened here is, as you can see, this guy, 31, moved here, and the new pivot is 5. So we're actually returning this new pivot as a, and what we just did is called partitioning. So basically means we did this funky logic where left and right sides you know, are swapped, and you know, we basically figured out what's the new pivot, right? So now the new pivot, it's going to be a function here called partition that's part of this sort, and that function will return the going to do what we just did, but it's going to return the index of the new pivot. So the index of the new pivot is 5. So now we know the value at 5 stays where it is forever, right? Because we know 33 is in the right position. We don't care if these guys are not sorted. All we care, they're greater. we don't care if these guys are not sorted towards each other. We know that they're smaller. Now, all we need to do is do the same thing, but we're going to return 5 and we're going to call the same quick sort on 2 subarrays, this and that, by calling a quick sort recursively with index 0 and 4, right? And then 6 and 8. So that's what's going to happen here, right?
I'm
Does that make
sorry.
sense?
Um,
Okay.
Can you please explain one more time on the line 5? Why did you switch 42 and 31? I miss it. I don't know. Sorry.
Yeah. So, it's a little confusing. So basically, when the left basically is greater than the right, that's when we swap the pivot and the left element. So index of the left element. So that's the step we just did here. So when the left element was 42, it kind of went over the right. So as we were going here, the left index kind of jumped over the right. And so basically, remember when we started this, we're saying at some point we need to insert the pivot kind of in the middle. So that was when the left element jumps over, that is the middle. So the position of the left when it becomes greater than the right is the position of the pivot. So then that's that place is where we're going to swap the pivot with that element. So this was 42 and 31. Our position was here, and we're basically saying swap 31 and 42, because we basically said the left was greater than the right. I think I had an equal, so I confused myself, as I said I will. And I'm sure I confused you guys. But anyway, so basically, at this position, we're remember the whole point of this was to kind of keep smaller elements generally on the right side, larger element generally on the right side. And then at some point, we'll need to insert the pivot here. So basically, we're at the position where we swapped the left element and the pivot. That's kind of the last step. And it's triggered if left is greater than the right. Cool. So then we do the same thing. So there are really 2 functions here. And the functions, so there's the quick sort, and you want to give it the array, right? And then you want to give it to so int left, int right. So that's what's going to basically give you the control over these indexes that we're messing with. And then there is a partition function, same array, and then left, right, pivot. So basically, when we kind of do this, there are two functions in play here. So the actual quicksort and the partition is what's going to give you the position of the pivot, so you can basically call the quicksort. So that's kind of the trick. So this partition is going to return pivot position. And that's going to be our partition. So as what we just did, that's the partition. Basically, we have a pivot, left, right. Here in the quicksort, we need to call partition, or say pivot equals partition, and then we pass those values in there, right? And then we say something like quicksort. So left partition -1. So that's the left, it takes care of the left side. And we say quicksort +1. So the right of the partition. Right, so here what we're doing, we just did what we just did. We returned the, we got to 31. We're gonna keep that in mind, right, where our new partition is. So that's going to be the trick. So this is, something we're going to cover in the code, how we kind of do that. So we'll take another pass through this with, with another example, and we're going to start writing some pseudocode around this. But kind of in the general, we're gonna, this is going to be our quicksort. We're going to be calling quicksort recursively, but we're gonna basically call the partition first to inside the quicksort to give us to organize our elements, and then give us the partition index. So then we go into quicksort on these guys here. That's kind of what we're, the left. So the 0 to partition -1. So that would be the 4, and then quicksort partition +1 here, right? So that's kind of the, that's really the quicksort here. So in quicksort, you partition, which is all that, stuff we did done here. You figure out the pivot. Right, and then you basically keep left side, right side, pivot here. Obviously we want to give it an array, right? And then we want to give it the initial, so left. Right, and then the pivot is going to be basically we're going to give it a logic. So partition is going to say, okay, what do you want to use as a pivot? So we want to say we want the last element of the array, right, as the pivot. So basically it's going to be the last element of the array as the pivot. How do you guys get the last element of the array?
Array length -1.
So something like this. So at the end, this is really the most critical thing, the partitioning. So as you can see, you're kind of partitioning these numbers, right? So logic there for the partitioning. We'll go through that, in a little bit more details and kind of get that clarity, right? The actual swapping. So it'll be more clear when we actually do the code and do the pseudocode for that. But the general idea is, as you saw, right, we're taking the list. The partitioning is all around, throwing these numbers around, right, in relation to the pivot that we're just basically passing to the partition. It doesn't matter which pivot it is. We can certainly do the array, the first element, the last element, 0 or last element. But, we're kind of going, and as you can see, that swapping lets you kind of roughly position them, and then when you get to a point where you step over, left steps over the right, this is when you're going to basically swap with the pivot. So you're going to swap 42 and 31 here. Once you stepped over, left stepped over the right, this was all right, we stepped over, and that's the next position we're going to do the swap. So that's the last. This is our exit condition. So exit condition means we are done. And when you get to the single element, right, when we talked about you kind of get to one element here. You're not gonna, left is going to be equal. It's not going to be greater. So there's, when you're going to pass to this, that you're going to hit that condition right away. So then you're not going to do any partitioning on a single element. So you basically, your partition is going to return right away. You're going to give it a same array, but your basically your indexes, what we're going to see, are going to be together like the same. So nothing's going to happen to the array, but array always gets passed, the same array. So everything you guys do, the array doesn't change. No new arrays. It's just same array, different left and right indexes. And obviously different pivot all the time, because that gets recomputed. All right, so give it a thought. Yeah, go ahead.
The exit condition for the recursion will be when left side index and right side index meet, when they're equal.
Left greater than the right.
Oh, when left is greater than the right. Okay, thank you.
So next time, take a look at this. Feel free to kind of look at it. Next time we will actually do the pseudocode for this, and kind of go through and start putting that in the code. We'll actually write the partition, and we're going to kind of put that in the code and see how that actually works with those two indexes and then the swapping. So it's it's a little funky, but hopefully you get the general understanding. That's all I wanted to get for you guys. Don't worry about semantics, kind of how these things exactly work when you swap things, but the semantics of it is what I wanted to get from this class, just the high level understanding of what happens in the binary sort, right? Cool. So to be continued next time.
Sounds good. Thank you.
All
Thank you
right,
so
guys.
much.
Have a good
Yeah,
class.
thank you. It's so interesting.
Yeah, very interesting and somewhat, challenging, right? That's good. It's making you think a little bit and making me think. So, all right.
Please share with your notes.
Thank you.
I'm sorry.
Share your notes.
Yeah, I will put them
Thank
in the Slack. So, and
Thank
if you
you.
guys can, start implementing that partition. If for bonus points, don't wait, right? Try to, if you have time, try to implement it. And obviously, all of this is available on the internet, but try to challenge yourself. Do it yourself if you can. Don't just copy, the code from Google. So otherwise, you're not gonna understand it. All right, talk later.
Thank you.